Welcome to the massive open online course on Aspen Plus. In today's lecture, we shall continue with the last portion of plotting relevant data on ternary diagrams, and we'll also learn residual curves, and then we shall go to the regression of data, collection of data from openly available data banks, and reporting relevant results on property sets. So this is the portion which actually is the last portion of this process and property analysis, because this portion we have already discussed in the previous lectures. So first we begin with ternary diagrams. As the name suggests, it is of three component system. There should be A, B, and C. Those who have worked on extraction system, you might remember that we have a triangular graph where the corners of the triangular chart have 100% A, 100% B, and 100% C. So any portion of that chart, it indicates a mole fraction of A, mole fraction of B, and mole fraction of C. So this is called ternary diagram. We can work on valid phases. Either it can be vapor liquid or it can be vapor liquid liquid. Two liquids, two immiscible liquids. Something like water and organics. Then we can identify the azeotropes. What are the azeotropes? Azeotrope is a mixture of two or more liquids whose proportion cannot be altered or changed by simple distillation. Basically, it's a constant boiling point mixture where the two components cannot be separated by distillation. So there are two types of azeotropes. One is binary azeotrope, another is ternary azeotrope. Binary azeotrope means when there is a two-component mixture which is inseparable, and ternary azeotrope means a point where three-component mixture is there and none of them are separable. So we shall learn about these ternary diagrams with this couple of examples. First, we take this first example. We have three components: water, octanol, and hexane. So we are asked to obtain a ternary diagram at 1 atmosphere pressure with 15 tie lines. Valid phases are vapor, liquid, liquid, because we have water, we have hexane, and they are not miscible that much. We are asked to use Nrtl property method, and we have to search binary azeotrope. So this is our task, the first task. For that, let us go to the Aspen simulation window. So first, let us add the components: water, octanol, and hexane. And the method, it is Nrtl. So choose Nrtl method and find out the binary parameters. Yes, all the binary parameters, temperature dependent binary parameters are there. And the source is, for octanol hexane system, it is VLE-IG. For water hexane, it is LLE Aspen, and water octanol, it is VLE-IG. As water and hexane, they are not miscible, so it is liquid-liquid equilibrium. So AIJ, AJI, BIJ, BJI, all of them are the parameters of the model. Now we have to bring the ternary diagram. So let us bring the ternary diagram over here. So this is the analysis tool. Let us bring the ternary diagram. We have water, octanol and hexane. All three components are there. Property method Nrtl. And it is 1 atmosphere pressure. So we do not have to change anything other than the number of tie lines, because we are asked to draw 15 tie lines. So instead of 5, let us write 15, and we are ready to run the analysis. So run the analysis. So it will take some time. Yeah. So analysis is done. So this is the ternary diagram that we were discussing about. So here we have 100% octanol, and this is the portion, this is the point where we have 100% water, and at this point we have 100% hexane. Okay, and we have a couple of azeotropes over there. So these are the tie lines we have: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 tie lines, 1 to 15, and we have 2 azeotropes. Now, where do we find that azeotropes? So one azeotrope is somewhere here. You can see one diamond-shaped azeotrope, and another azeotrope is hidden somewhere here. Now, if you want to know the point at which the azeotrope, or what is the mole fraction of components at that azeotrope, you can just go to this azeotrope condition and you will find over here both the azeotropes are binary, because in both of them the third component has 0 mole fraction. Okay, so at 99.5 degrees centigrade we have water and octanol azeotrope with no hexane, and at 61.43 degrees centigrade we have water and hexane azeotrope with no octanol. Now this azeotrope is very well visible in the ternary diagram. Here we see 21% of water and 79% of hexane. So you just go to this place, you'll see here 0.21. This is the point 21 of water, and hexane is 0.79 at this point. And we do not have any octanol over here because the azeotrope lies on this line. This is the 0% line of octanol. So this is the first example that we have, and we have a second example of ternary diagram where we have water, ethanol and cyclohexane. Here also we are supposed to obtain the ternary diagram at 1 atmosphere with 15 tie lines. The valid phases are VLL, vapor, liquid, liquid, and we are supposed to use Unifac property method. And there is a ternary azeotrope, we have to search for it. So for that, let us open a new simulation. So we have water, ethanol and cyclohexane. So let us write water, ethanol and cyclohexane. So actually we are looking for this particular component. So add the selected component and let us rename it. We write it here cyclo H or cyclohex. Okay. Now we are supposed to use Unifac property method. Press next and run. So property calculations are done. Now again we bring in the ternary diagram. Water, ethanol, cyclohexane, Unifac property method. We have 15 tie lines. Run analysis. So we get another ternary diagram. Shape and nature is same. But here you find there are 4 azeotrophs. 1, 2, 3, 4. One of them is very clear at 0.3. Okay? Other 3 are hidden somewhere. Anyway, let us go to the azeotroph concentrations. Yeah, so we have 4 azeotrophs. The first, third, and fourth, these azeotrophs are binary azeotrophs because in these azeotrophs you have one of the components having 0 mole fraction. That means that particular component is absent in the mixture. They are binary mixtures. But the second azeotroph is having all the 3 components, water, ethanol, and cyclohexane. It has 15% water, 31% of ethanol, and 54% of cyclohexane. And that azeotroph is available at 62.39 degrees centigrade. Okay, so that's how you can study the ternary diagram and you can map the azeotrophs. Whether it is binary or ternary, you can find out the azeotrophs. Next, we will learn about the residual curve. Now, what is residual curve? This analysis is used to generate residue curve maps. And these maps plot the composition trajectories of ternary mixture undergoing distillation at total reflux condition. Now the question is, what is this composition trajectory of ternary mixture? Basically, if you have a container having 3 components, A, B, and C, is a mixture of 3 components, and it is open, then as the time progresses, A, B, and C, they get evaporated, right? So initially, the mole fractions of A, B, and C will be, say, X1, Y1, and Z1. Total, it should be 1. The next moment, as the components A, B, and C, they evaporate, they will not evaporate at the same rate because components A, B, and C, they have different volatilities. So the more volatile components will evaporate faster than the less volatile components. And then the next moment, the composition will be X2, Y2, and Z2. Then after some time, it will be X3, Y3, Z3, and so on. That means, as the time progresses, the residual liquid will have these compositions. Okay? Now, if we plot them, suppose if this is the initial composition, which is x1, y1 and z1, the next moment if we plot over here, this may be x2, y2 and z2 and so on. The next composition may be somewhere here. So we can safely plot a trajectory. So from the initial condition to the final condition, suppose it will end over here. Where it will end? It will end at the lowest volatile component, because in the residual curve, the last drop of the liquid which will get evaporated must be the least volatile component. If it is A, then the mole fraction of the last component will be 0, it should be xn 0 and 0, where xn is equal to 1. That means this is the pure A that will be evaporated at the last. Okay? So this particular trajectory is called the residue line, residue curve. And if we start from different initial points, we will get this curve, this curve, this curve, and so on. So that particular map is called residue curve map. And these maps are also used to visualize the presence of azeotrope in the mixture. Okay. Now we will take the example of ethanol water ethyl acetate system and find out its residual curve at 1 atmosphere pressure. We have varied phases, vapor and liquid. Now here everything is water soluble, both ethanol and ethyl acetate. All of them are soluble in each other. So we have only one liquid phase. So one vapor and one liquid phase. We will use Nrtl property method and we will draw 10 to 15 curves. So for that, let us again go back to our Aspen Plus window. So you have water, ethanol and ethyl acetate. So water, ethanol and ethyl acetate. Find it. Yeah, we are looking for this particular component. So add the selected component. Let us rename it as ethyl acetate. Okay. So we are supposed to use Nrtl method. So place Nrtl. Run next. Binary parameters to be calculated. Yes. Now you have to bring in the residue curve. So bring in the residue curve. We have water, ethanol and ethyl acetate at 1 atmosphere pressure. Varied phases are vapor and liquid. And we are supposed to have 10 to 15 curves. That's what it has been asked. So run analysis. So we have 15 curves, curve 1, curve 2, curve 3, curve 4, and so on. Okay. So this is the residual curve that can be generated from residual curve method. Okay. Next, we will learn what is data and how to do the regression. Now, you already know what is regression. Suppose if you have a vapor-liquid equilibrium data, x versus y, and if you say your vapor-liquid equilibrium equation, the model equation is, say, a plus bx plus cx square, and so on, up to cx square, then you have to put the values of x and y data on that and find out the values of a, b, and c, which are the model parameters. And this is called the regression. So you have to have a data set, and you can do the model regression based on that. Now the question is, from where you will get the desired data set? Obviously, you can say that it will be obtained from experimental data. So you can do the lab experiment yourself, gather the data, and that you can use for regression. But Aspen has a long-term collaboration agreement with NIST. What is NIST? It is United States National Institute of Standards and Technology. So this NIST has a huge database of thermodynamic properties, transport properties, and phase behavior of a lot of components, maybe around 24,000 pure components and around 30,000 binary data mixture. And the good news is that it is absolutely free for Aspen Plus users. You do not have to pay anything for this data. I will show you how to gather the data from NIST database. You will get this data: azeotropic pressure, binary diffusion coefficient, binary liquid-liquid equilibrium composition, vapor-liquid equilibrium composition at isobaric and isothermal condition, the critical temperature and pressure, density, enthalpy, and all sort of properties that you can think of are there in NIST database. Now, NIST database, they are broken into 4 blocks. These are the blocks: phase diagram block, volumetric block, energetic block, and other block. The name suggests phase diagram block, it will have triple point, critical temperature, phase boundary pressure, etc. Volumetric block has density, saturated and single phase density, volumetric coefficient, and energetic block contains energy differences, energy derivatives, speed of sound, etc. And other data block contains transport properties, surface tension, refraction, and so on. So this is about NIST. Similarly, there is another database which is called DKMA, and it is an abbreviation for a German term which loosely translates into English as German Society for Chemical Apparatus. So it also has a lot of data, but the problem is it requires subscription. You have to pay per dataset online purchase, not free of cost. Now I will give you an example of how to retrieve the data from NIST TDE and DKMA binary data for water ethanol mixture and how to save the data. For that, let us go back to our Aspen Plus simulation window. Here you will find the data source: NIST, DKMA, and DIPPR. So DIPPR is the common data source which anyway you use always. DIPPR comes along with the Aspen Plus software, but NIST and DKMA should be downloaded online. So for that, you just add NIST. You click NIST. Suppose you want a binary mixture of water and ethanol. Yes, water and ethanol mixture, binary mixture of water and ethanol. Retrieve data. So it will take some time to retrieve binary experimental data. This may take a few minutes, you have to wait. Well, it didn't take that much of time. Anyway, we are happy. And we get this binary data. So if you see binary VLE, suppose this is the binary VLE 037. You have so many data set. VLE 0032 320. Okay. Now, if you say that I want to catch this data and say this data, binary VLE 049. So here also you can find the temperature versus liquid mole fraction of water and vapor mole fraction of water at this particular pressure. So the pressure is 101 kilopascal. Okay. And from where these data have been extracted, it has been said Jones CA. So this is the author, and source is Industrial Engineering Chemistry 1943, volume 35. So the title of the paper is Equilibrium Still for Miscible Liquids Data on Ethylene Dichloride, Toluene and Ethanol Water. So this is the article from where this data has been extracted. Now suppose you want to save binary VLE data 037, which has been taken at pressure 66.6661.2 Pascal. Okay, so here you have to say save data, and here you have to choose VLE 37 and VLE 49. Okay, so press OK. So the moment I press OK, here you will have the data set will be saved over here. So press OK. Here, two data bank has been opened. The first one is water ethanol. These are the data. Okay, so this is the data set. And for the second data set, we have the similar data set. Obviously, it is at different pressure. Anyway, let us try to find out the XY diagram. So for that, this is Y versus X. Okay, so we have water ethanol mole fraction. So this is the vapor liquid equilibrium curve, and this has been obtained from this data set. Now let us take this one, the second data set. Here also we can generate one plot. Okay, so here also we got another plot of water ethanol. Now we have two plots. Now we want to compare them. We want to see whether these two plots match with each other. Let us try. For that, we will merge the plots. Let us merge the plots. Do it with a single y-axis. Yes. Now you can see it has merged. Now, so here we have the data for both the experimental data set, and all of them, they come within this line. So that visually gives us a confidence that both the data sets, they have reliable data, because one data set has been obtained from a paper in 1943, and another data set has been obtained from somewhere else, and both of them have got similar kind of data structure. So we can rely on this data set. Okay, so this is how we bring in the NIST data. Similarly, we can go for DKME binary data. For that, we have to click in DKMA, and we do not select this one. We select only water and ethanol and vapor liquid equilibrium of the mixture. So it is searching DKMA DTherm on web. So it will open the DTherm on the web. So Aspen has its own web browser where it will search. So just increase it. Okay. Now you can see that we have isobaric vapor liquid equilibrium data, both isobaric and isothermal, for the system ethanol on water, published in different years within this temperature range and pressure, and so many lines. What does it mean? Lines means each and every line has a pair of data. So 8 lines means we have 8 pairs of XY data. For 71 lines means we have 71 pairs of XY data. And you can understand that as the number of data points increase, the price also increases. So for 6 points or 8 points, we have only 59.5 euro we have to pay, whereas for higher amount of data we have to pay 142.8 euro. So in order to purchase, you have to first register yourself and log in, and then you have to select, suppose you select this one and check out. So it says one item is there in the cart. You may say order. So here you have to log into your system. Once you do it, you will be given the option to pay. You have to use your credit card and you can pay and get the data. Now we have something called tab poly. As the name suggested, tab poly means it is tabulated data using a polynomial. Okay, so either polynomial or tabulated data. Actually, when you have a user-defined conventional component which is not available in Aspen database, then you can enter certain data and you can set a characteristics of that particular component in your database. For instance, suppose you have an user-defined conventional component called compx. The name suggests that this component is not within your Aspen database. So you are giving it a name, compx. So how to use tab poly for that? So let us go to simulation window once again. Let us user define compx. Okay. So this is our component ID. So we press finish. So it doesn't have any component name, obviously. It doesn't have any alias also. Let us not bother about that, because we have to give certain data to it so that there is some characteristics that can be obtained. For that, you have to go to method and click tab poly. And here, create a new ID for tab poly. And the property you can choose over here, what kind of property that you want to feed in to this compx. For instance, we have vapor pressure versus temperature data in tabular form. So we want to feed this data. So we have several options, but we will choose vapor pressure data because we do have this data to feed in. Okay. Now we have to set a property method. Let us choose a property method first. It is Nrtl property method. So Nrtl. So choose the property method Nrtl. Here also we have few options for data generation option. Data generation from user input enthalpy or heat capacity data. So you can generate Gibbs free energy data, or you can generate entropy data, or you can generate both, or you may not be willing to generate any data. For the time being, let us not complicate the matter and do not generate anything. So go to data. So here you have to set the component first. So we have compx. So we have to give the vapor pressure data for this component x. Okay. We can give it in tabular form or in polynomial form. Polynomial form means it will have y is equal to a1 plus a2 x square plus a3 x cube up to a8 x to the power 8. So this is the polynomial model. We have the minimum and maximum temperature for this model is also given. But we do not have polynomial coefficient. So instead we will give tabular data. And once we give the tabular data, Aspen can calculate the polynomial or it can extrapolate. So let us go and check the data. We have temperature at 0, 20, 40, 59.4, 100, 160. So the temperatures are 0, 20, 40, 59.4 and 100, 160. So 100, 160. Similarly, the values of vapor pressure we have 70, 177. So it is 70, 177, 390, 760, 390, 760, 2358, and 8200. So we have the vapor pressure data that we have fed in to the identity of compx. So from there, Aspen can estimate for comp X. Now, similarly, if you have some other data, for instance, if you have the data of, say, surface tension or vapor thermal conductivity, or you may have data of liquid viscosity. In such situation, you can again go to tab poly and create, say, liquid viscosity. Choose liquid viscosity for Nrtl method. In dataset, you choose complex tabular data. Now at various temperature, you can give the values of liquid viscosity. Okay, so like that you can add the tabulated data or polynomial coefficient for comp X, as much data you can give. So more and more data you give, Aspen will have less effort and more accuracy in characterizing the unknown component that you have defined.